Give a warm welcome to Neville.
Morning, everyone. Today's talk is going to be about powering crowdsourcing of public transit delays with Rust. Morning, everyone. My name is Neville Dipale. Sorry about that. My name is Neville Dipale. I'm from South Africa. My Twitter handle is Nevi_me. I'm working as a data engineer, so mostly a freelancer. I started programming as a hobby about 10 years ago now. I run a public transit information service in South Africa, so mostly in my region, Gauteng. I started using Rust about half a year ago, and I recently, as in a few months ago, became an Apache error committer, contributing to the Rust implementation. Okay. So in our agenda today, we're going to be talking about trains in our region and challenges with them. So I'll give you an overview of how they work, etc. I'll talk about the crowdsourcing solution, how we use Rust, and what the benefits of having used Rust are. So as a background with our train service, we've got 2 train services in our region. Out of interest, how many people have been in South Africa by a raise of hands? Oh, thanks. So we've got two trains. We've got the fast train and the metro train. The fast train was actually built for the 2010 Soccer World Cup. We hosted it, didn't win it. The metro train has been around since around the 80s, so it's got very aged infrastructure. They haven't replaced some of the trains in quite a long time. The metro train is very cheap, where you can get from one side of the province to the other side of the province at about 2 to 3 euros, and then most trips will be 1 to 2 euro. When the fast train is a bit more expensive, so it goes from the airport into the city, and you pay about 10 euros at times for the train. So the metro train is used mostly by poor communities and students who rely on the service. So let's guess which train is which here. You've got this one, which would be bus train, and then you've got this one being the metro train. So we've had this problem for a very long time where, because there aren't enough trains, they get overcrowded and people get desperate to get to work, and then they hang on to the trains. They are changing that now with new metro trains, but we've had problems over the years with procurement, government issues, etc. We were supposed to have these new trains about 4 years ago. I think now there's only 3 running, and they've promised that we'll have all of the trains being replaced by these ones in the next 10 years. So the struggle is still going to continue. Okay. So with metro train delays, they've got severe infrastructure issues, as I've mentioned. It's estimated that 40% of rolling stock, i.e. the train coaches, are out of service, are not available, and this affects peak time services quite significantly. It's only during the day when there's fewer people taking trains, fewer services, where they get to catch up, and then the same problem then begins again in the evening. The trains can get stuck in the middle of the tracks, cable theft, signaling problems, etc. It's not uncommon for you to be on the train, stop in the middle of nowhere for like 15 to 20 minutes, and then the train continue again. So I did an interesting analysis, not here though, for something else, where we were looking at the average train travel times based factoring into account the delays. And one of the trains took about, I think it traveled at 30 kilometers an hour effectively, and it was traveling about 100 kilometers. So you can imagine how long that train trip was. Commuters experience delays with over 60 minutes in most cases. Part of my pitch was, I said, it was quite dramatic. I said, your train is arriving in 20 to 90 minutes. Because that's a kind of uncertainty that people end up having. There's communication issues also from the operator. We don't have, none of it is digital. All of it is analog. We don't have an API that provides information or such. And a lot of the times, even for the trains to move themselves, they rely on phones. The train conductor will stop the train and say, can I move on? And then they have to wait for like 10, 15 minutes or so. In the past few years, we've actually had a number of collisions of trains. There was one big one where I think 20 people died or so. So it's been very bad over the years. Okay. And then here's a graphic that just shows some of the data that we've collected. I've split it into delays. It's a histogram of delays where each bucket is 5 to 10 minutes. So the first two buckets there are the trains that are early or on time. And in the 10-minute category, you've got 53% of the trains being delayed by up to 10 minutes. So this is great, but also bear in mind that we don't crowdsource the entire network. So it's only a snapshot of some of the trains. And then you'll see that the delays sort of go down. I think this would be a log normal distribution. So you still have quite a number of trains that are very late in most cases. And each time, this is normally either in the morning, somebody has to get to work or a meeting at 8 a.m., they end up getting there at 9. As a result, a lot of people have actually lost their jobs because you'd come late every day in a week and then your employer just says, well, sorry. There are people who wake up at 3 a.m. just so that they can get to work at 8 a.m. in the morning, which is quite terrible. And then the same again happens at night where people would leave work at 5 p.m. if you work at 9 to 5 and then only get home at 10 p.m. Okay. So our solution has been to provide metro commuters with information on train delays. We use Twitter and push notifications on an Android app. So we've got an Android app that people use to crowdsource this information. We crowdsource the delays either by sharing a train trip or spotting trains. So if you would have noticed on the first, on that picture of the metro train, there's normally 4-digit numbers on each train, and we use those. We map them to the schedule, and then people just provide us what the train number is, and then we figure out which train it is. We calculate the delays based on the actual versus schedule. So the actual algorithm is quite simple because we're just currently using a linear model where we say if the train was supposed to be here 5 minutes ago and the average speed has been, let's say, 20% less than what it should be, we just do a simple linear progression of what the delays would be. And then we generate estimated arrivals at train stations and then notify commuters about delays. So this is what we use Rust for. Okay, so in terms of submitting train delays, the architecture is quite complex. There's a lot of services that are running around because I've been doing this for about 7 years now. Some of the stuff is in Rust, a lot of it is not in Rust, but for the talk, I'm just going to talk about the few components, specifically 3 components that are built in Rust. We've got a location sample service that checks for sample validity and accuracy. So imagine when you're crowdsourcing, one of the problems that you have is that some information might be accurate, some might not be accurate. There's nothing stopping a person from saying I'm on train 1, 2, 3, 5 instead of train 1, 2, 3, 4, and then they give you incorrect information. One of the things I saw in the early days of deploying this was a train that was moving in reverse. And it took me a while to figure out that, oh, somebody's actually on the other train, but they're submitting train locations for this one, so it looks like the train just keeps going backwards. Then this location sample deals with that. We've got a service that then it saves the samples in the database. I'll explain a bit more in detail about that. Then you've got a vehicle stream service. If you were in Rust Lab in Italy, I talked about specifically the vehicle stream service. It calculates delays samples every 7 seconds and then generate locations and delays of trains. The user sent delays from samples, and then other users are notified of delays. I'll talk about this in detail. So here's an example of the process. So let's say you've got train A that's expected at station 3 at 8 a.m. There's no samples yet, so we're just relying on schedules. A user's waiting for the train, different users are waiting for the train at station 4, 5, 6, 7. And then those are the estimated arrivals at those stations. So once we receive our first sample, let's say the sample is at 8:12, and then that's between station 3 and station 4. Already, for station 4, there's a delay, so we'll just project those. And then I've marked them in red to show the users that we're notifying. One of the problems is that we don't want to spam users and notify them every other minute to say, well, the train was arriving in 4 minutes, now it's 3 minutes, etc. So we project those, and then at the next sample that we get, we only then calculate the difference in delays. If the delay is still more or less the same, we use a 5-minute range, we don't notify the user again. So when we get a next sample at 8:16, we'll then say, well, the station 4, the train has already passed, it was at 8:14. In the next one, it's at 8:25. It's within a 4-minute difference from 8:21, so we're not going to notify the user. And then we're only going to notify the user whose train is now arriving at 8:33. Okay. So in terms of the Rust services themselves, the location sample is a gRPC server that uses Tower gRPC. It receives vehicle samples and then just processes them. It matches samples to trains, so we take the 4-digit train number and then we match it to the train and then we generate a last known location. It uses Actix to monitor the state of the users and trains. I'll talk a bit more about what I use Actix for. I know Actix Web is more popular than Actix itself. And there I've just shown a screenshot of a trip executor. It's effectively the state that I manage for the application. Okay, so we've got a trip status struct that tracks the last known details of each trip. So going back to the previous slide there, you see that we've got user trips and trips. A user trip just matches the user to say the user is on this train. So when they submit another train sample, we automatically reject it because you can't be on two trains at the same time. And the trip just tracks the overall status of a trip. So in the trip status, you'll see we've got the trip ID, the route ID, the last distance, and then location and other information. The last distance is very important because we calculate the distance based on the geometry of the trip. So if somebody submits a sample and says that the train is close to station 3, let's say it's 2 kilometers away from station 3, and another user submits a sample 5 minutes later saying, actually, it's close to station 2, we're going to reject the second sample because the train can't go back in reverse. So that's how we work around that issue. And then we also keep track of congestion and occupancy. It's what Google does. We're hoping that with a lot of users, then we can be able to reliably tell people that your train is actually full. It's better maybe to wait for the next one if it's coming. Okay, so we've got an Actix actor that receives a sample and handles it. The benefit here is that I don't have to worry about multi-threading because Actix has a mailbox that just stores samples. So as long as I've got a big enough mailbox to handle capacity, then all the samples just keep coming and getting processed. One benefit of Rust is that it's very fast, so I never have a big backlog at any point in time. The sample just produces a location or an error if there's an error. For example, the location is invalid. Okay, so after the service saves the valid sample onto the database before it returns it to the client, this sample then gets picked up by the next service that I'm going to talk about. And here's how a sample looks. If you work with geospatial data, it lists vehicle coordinates and then some information about the vehicle. Okay, so the next service that I then use is the vehicle streams. So the streams just reads data from a database periodically every 7 to 10 seconds, and then it projects the delays per route. So this is for estimate and live scheduled services and live services. It just calculates the estimates and keeps churning them out throughout the day. It starts running from, I think, 2 a.m. when the first train moves, up until 11 p.m. when the last bus is moving. So it's both for trains and buses. It sends all the results to a pub subservice. I use nets.io for that. And then there is just, it uses Tokyo. I just use a Tokyo interval and run it every 7 seconds to generate my sample. Okay. So how does Rust help with vehicle streams? The service has evolved quite a lot. I first wrote this service about 4 years ago. And I initially wrote it in JavaScript where a small crash would just collapse the whole thing. I moved it to Kotlin in the JVM, hoping that it'll be better, but then I had to keep throwing more RAM at it. If you're at Rust Lab, you remember I talked about going from using 20 gigs of RAM to less than a gig of RAM at peak time. So it took a few months to rewrite it in Rust. This was actually when I was still learning how to use Rust. So this was about 14, 15 months ago. And I'm seeing very impressive performance. I previously talked about how the service just runs for months on end. I never need to restart or anything. I use a third of the CPU usage than before. I talked about the 20 gigs of RAM going down to around 500 megs of RAM. And the main benefit here is that I was able to replace an in-memory cache with a simple hash map. I'll talk a bit more about this. And then the service is easier to maintain and extend. And then there's a notification service because I mentioned that users have an Android app. So when one user is submitting samples, other users are relying on that sample. It's a Fire-based cloud messaging service. I recently found this Crate FCM. I think it was abandoned effectively, but somebody picked it up and started using it, which is also one of the nice things about open source in general. It notifies users based on a range of things. I've got an enum there that just shows the different type of alerts. So it's effectively a generic cloud messaging app where I can just keep on extending it by different types and then send them out. So it's not really train delay specific. We we personalize the information for individual time delays. So if you've got 5 people waiting for the train at different stations, and you notify one user now, but the delay doesn't affect the other person, when it does affect the second user, you only notify them. So we sort of keep state of each individual user and when last we notified them. Because one of the things we try to avoid is spamming users by sending them 100 notifications per second, because immediately someone's just going to delete your, uninstall your app, and then you're never going to see them again. Okay, and then the service also uses Actix, but instead of using gRPC, we use nets.io. So within the whole architecture, there's messages just being passed around quite a lot. I used to use Kafka, but now I moved it to net.io. A new subscription from users are added in real time. The nice thing with subscriptions is that a user says, I only take the 7 a.m. train, or I only take trains from 7 a.m. to 8 a.m. and between station 7 and station 24. So once the train passes station 24, we don't notify you about anything because it's no longer relevant information for you. This is also one of the nice things, because the fast train service that I talked about, they will send you a notification about a bus in some faraway place not running, and it just irritates the poor user experience. All transit data state is loaded at startup when the application starts, and I keep it in memory. So static data like what the train numbers are, what the stop locations are, etc., as well as the trip data. The benefit here is that we end up storing everything in memory, because the application effectively, as long as the application doesn't crash, which is one of the benefits of Rust, it'll keep running indefinitely. So if you use Actor systems quite a lot, you'll know that some Actor systems support snapshotting, where once periodically you'll save the user state onto a database so that the application crashes, you can recover that state. Here I sort of cheat because I don't use that. I just load everything in memory and keep it running from there. So why Rust then? The main benefits are that I'm really getting stability out of this, because being able to write a program where I can prove to myself or to the compiler that it won't crash, and I handle every state that could cause a panic, helps me to create a cheap in-memory store using a hash map, for example, instead of bootstrapping Redis or Memcached or something else. So you'll notice that I don't really use Rust for something very novel per se, but it's really just to give me the stability and the performance. Actix has been very good to avoid concurrency issues, so it makes it easier to think about a lot of things. Interestingly, I rarely ever have problems with borrow check or lifetimes or everything, because everything is quite simple effectively. The cost saving is the important element for me, because this is a hobby, and maintaining this means, well, if I was doing it as a profession or whatever, I'd have to wake up at 3 a.m. in the morning to notify users of cancellations of trips and all of those things, and then stay up all day until late at night. Because it's a hobby, it's very costly. Every hour that I spend on this is an hour that I could be working as a freelancer and putting food on the table, etc. And also the other thing that I save on a lot is server costs. Initially, about 2 years ago, before I started using Rust, I had to have a 64 gig server, because the Kotlin service would use about 20 gigs of RAM, and then all the other services would cumulatively add up. So I used to normally run at about 40 gigs of RAM usage, just running this aspect of this public transit stuff. And now the services that I just talked about in Rust, including others that I haven't mentioned in this talk, I can run all of them in a 1 gigabyte container with 2 CPU costs. So that's significant for me. And then the other thing is scalability in terms of performance. Right now, talking that I use 2 CPU cores, I actually use very little. And if we were to expand the services, maybe even 10-fold or even 100-fold, I'd still be able to use them within the same resources. Okay. That's it from me. Are there any questions?
Oh, thanks for the interesting talk. By the way, I already saw you in the Rust lab. That's amazing. About the scale of the thing, so how many users does this service actually serve concurrently? And what's the frequency of the notifications and messages to and from users, just to get an idea?
In terms of the number of users, we get about 100 users a day submitting samples. Then there's a lot more who receive samples. So it's not very frequent, and it's only really busy in the mornings when a lot of people are taking the trains, and then again throughout the day you'll see one sample once in a while, but it's not a lot. And then in terms of notifications that are sent, there's a hard rule that says that we won't send a notification to someone for the same train within 5 minutes. But we send about, I think the last time I checked, it was about 500 notifications per hour at peak times. So it's still quite a young service.
Any other questions?
You, again, very interesting talk. You mentioned you run it from about 3 a.m. till late in the evening. Does that mean you can shut down your service? And if you didn't have that option, would you have to change anything about your infrastructure?
So in terms of running it, the running aspect of it is a warm body standing on a chair, looking at train delay, cancellations more than delays. The whole delay infrastructure is automated. It's the cancellations where there's a WhatsApp group from the train operator where they say this train has been cancelled, the train isn't. So those ones we can't automate as yet. We have to capture a cancellation and send that out. Everything else is just automated. So at night when it's based on schedule, so if there's no scheduled trains that are running, the service will just keep calling every 7 seconds but do nothing. And then once the activity picks up, it starts running. So it always runs 24/7.
Hi, great talk, by the way. I was just wondering, does the app send regular updates, or does the user have to actually send the update themselves, press a button or whatever?
Oh, my apologies. I actually didn't talk how users submit. So there's two ways that users do it. First one is average of a user's wait for a train. There are about 3 trains will pass by, depending on where they are. In the main central stations, there'll be a lot more. So when a train passes by, you can spot the train by saying, I just saw train 123 passing by. And then we use that one-off sample to calculate. But then once you get on the train, similar to if you've used Waze, it's something similar, where once you get on the train, you can say, I'm on this train, and then it'll take a sample every, I think it's between 45 and 60 seconds. That's how we get the sample. And then once you get off the train, it stops submitting.
Thanks.
Very nice talk. So you mentioned you store the state as a hash map in memory. Have you ever had the issue that the state got too big and you were not able to forget? So something you get using Redis and Memcache is TTL, so you can forget an entry automatically. Do you need to handle that in your application, or is that not an issue?
So I use both. There's a trait called TTL index, I think, I can't remember. I use that for state where I want to keep stuff for a short life, specifically on the vehicle service. The reason why I use hash maps for the others, that it's static information that doesn't. So if I restart the application once a month, I'll just load that information and keep it in there month. I do incremental updates where there are changes that happen. And then in terms of the application getting big, so right now with about 7,000 services, 7,000 different routes, and 7,000 vehicles. I use less than a gig. So in the vehicle stream service, I use about 500 megs, and then the first service, which keeps static information, I use about 400 megs. So if for example, I were to increase the services by 10-fold, I'd still be able to handle it in, let's say, 10 gigs of RAM. So that's not a concern.
Do you have train spotters in South Africa? And could you maybe change your app a little bit so that it gamified it for train spotters?
Well, there's a lot of stuff I didn't talk about, and I see there's a lot of questions about it. So one of the things we do on the app is we keep track of how many we've created a point system for train spotters, where based on how much the train still has to travel, you'll get more points. And if there's no similar information. If you're the first person submitting that, you get more points. At the end of the month, because a lot of the people are often students, etc., we buy them data and small prizes that I can afford. It's out of pocket. And then the other one is we keep track of how many kilometers in total you've traveled. And we also incentivize those people. So we do gamify. Because otherwise, people don't see the benefit of spending their data helping sharing information, even though it helps.
More questions? I don't see any.
Do you know if the train drivers use the app as well, or are there any plans for like the company to use it?
Some background. One of the problems we have in our country is that the government outsources a lot of its services through a tender system. The problem with that is that even when you are coming with good intentions, trying to help out, they can't just take your services. They have to go through procurement processes and all of that. So that's one of the challenges. We have put in a proposal a number of times where we said, instead of putting GPSs on trains, because the trains are old anyway, and they might get vandalized, let's create an app for train drivers, because all train drivers have smartphones. And then those drivers can, when they get on the train, they can say, I'm logging in on train 124. One of the problems, though, that we have, because we've tried that with buses also, is that bus drivers are very unionized, so there's a lot of organized labor, and there's always issues about whether this information will be used to the prejudice of drivers. Because sometimes the drivers aren't very honest, in the sense that when a bus is supposed to leave at 9 a.m. or it leaves at 9 a.m. every 15 minutes, sometimes the drivers will intentionally not leave at 9 a.m. and leave in a bunch together. So if you know public transport theory, I think the concept is called bunking. So there's quite a lot of issues that work against us trying to implement that. But we are trying to get it done, because if we do that, then we don't need to track things.
Anyone else? Okay.
Thank you.
Thanks, Neville, for your talk.